welcome to another episode of Data Skeptic Animal Intelligence. Today we're going to talk a little bit about how we can model biodiversity and take some measurements and come up with good predictions about the species you might find where. Well, Becky, do you think that's a fair description?
Yes, I do. So when we talk about biodiversity, when I'm teaching it to students, we talk about two things, richness and evenness. So how many species are in a given place and how many of each species are there. Because if you have 20 species, but only one of them makes up 90% of all your observations, well, that might not be great biodiversity. So we're looking for combinations of richness and evenness. And we can predict a lot of these things, like if we go out and find a certain butterfly or a bird, and we know it's always with these host plants. It's always at this elevation. It's always around this temperature. Well, then you can pull in all this abiotic data and start making predictions like, okay, maybe we're a suitable habitat for this animal. Or if you're strictly looking at biodiversity and not a single species, you can start to model where might our hotspots be. This is a big data problem. It's really important in terms of maintaining ecosystems and ecosystem services. So this was just a very cool topic, and it's a tough one, I think, for scientists.
When I think about, I'll go for hikes quite often, and something that strikes me is I'm aware that I'm unaware of how many species I'm passing. Like if I had the eyes and the wherewithal to catalog, I'd probably be able to tell you I saw, 100 species, even, out here in the desert walking around or something along those lines. But I don't have the cleverness to spot them because, many don't want to be spotted, or at least that's my impression of it. And I don't necessarily know what I'm seeing. It's hard to catalog. It takes pretty trained eyes. Do you think those limitations are really impactful to the quality of measurements we get?
I think they can be because you need a good data set of where you find a plant or an animal before you can really build any predictive model based on abiotic and other biotic factors. So, yeah, I think that is a big challenge is getting that data correct and being able to build your models off of that. We're certainly getting better at it with machine learning, identifying animals and plants automatically in images. So I think it's just going to keep getting better and better, but definitely I think that's hard.
Is there a set of categories that you would put this data into?
Yeah, so some of the trouble with modeling species distributions is you don't always have presence absence data. So that takes a biologist like me walking on a piece of land, or maybe I'm out on a boat, something like that, and I'm measuring, okay, the species I'm interested in is here, but not here. Some of our biggest data sets are not like that. They're presence only. It's just you on your hike and you happen to see something interesting and take a picture, upload it to a place like iNaturalist. So presence only data, we have a lot more of it, but it's really tricky because it's going to be biased towards trails, it's going to be biased towards city centers, anywhere where there's people. So when you're trying to build predictive models with these big presence only data sets, you're going to have to find ways to deal with that bias because you're going to be working with a big multivariate data set and you need to figure out which signals are actually the most important, because being close to a trail might not actually be all that important if you're trying to predict where some organism occurs.
Are there clever correlations we could take advantage of? Like, a certain insect that only eats one thing needs to be near that particular vegetation or needs to be near water or things along those lines.
Absolutely. If you can start to figure that kind of thing out, especially those abiotic factors, then you can start getting much more powerful predictions that aren't reliant on these observations that are just wherever the humans happen to be looking. So that's very helpful. And we're getting better with like remote sensing with satellite imagery, looking at temperatures, different types of vegetation. If you're able to get some drones, you can fly and do photogrammetry. So now you have like a big 3D data set of vegetation that you can start using for data. So there's lots of different ways to get that information.
All this data and we still haven't found Bigfoot.
I know, right? It's almost like maybe Bigfoot's not out there.
Well, presence absence.
So my name is Hager Radi. I work at Mila as a senior applied scientist. I got my bachelor degree from Egypt and my master's degree from University of Alberta in AI and specifically reinforcement learning. But I've been bouncing between different research areas in AI, like RL, computer vision, NLP, and so on. I do industrial AI research and sometimes academic research. yeah, I work on different research areas between NLP and LLMs, computer vision, biodiversity monitoring, and yeah, like the work we're going to talk about today.
And what brought you to that point? What was your original academic interests?
So this specific project was part of collaboration between me, my team, and David Drolnick lab at Mila. They work on this. They had a group of students working on this, and I joined them. It has been like more than a year and a half, and yeah, I really enjoy it. We're still working on the project. There is more follow-up work on the paper we're discussing today.
RL has had, some exciting things in the past, 10 to 15 years with like DeepMind results and other stuff like that. Are there particular areas of reinforcement learning that are most exciting for you?
For me, I was specifically looking at real-life use cases for reinforcement learning. It was like a specific use case on medical data, predicting mortality rate for on like sepsis disease. It proved to be quite helpful in that use case. RL is exciting. Maybe now, like with the LLM hype and everything, it's not as present, but actually it's being used in reinforcement learning for RLHF. It's quite helpful now in LLMs. I like focusing on real world use cases in my research.
Well, an interesting real world use case is the one you cover in predicting species occurrence patterns from partial observations. Could you share a few details on the project?
So the goal of the project was to do biodiversity monitoring. Biodiversity is being affected by climate change. For example, like more than half of the US birds are in decline. 1 in 4 birds disappeared in the past 40 years. The number of butterflies in Western US has declined by half in the past 40 years. Given all the changes in climate and environmental changes, biodiversity is being affected. And it's important to maintain healthy ecosystems because it's important for human life and human well-being. We need more work on that, and machine learning is offering a huge opportunity to have impact on these areas wherever data is available. And given the availability of data now, like remote sensing data, satellite images, and citizen science data, it offered an opportunity to dive into this area and try to draw an impact.
Well, you touched on 3 of the different data sources we could use for biodiversity monitoring. Could you expand, I guess, maybe first on remote sensing? What kind of data is available there?
There are climate data. There is a database for climate data called WorldClim. Data like temperature, humidity rates, and so on, which is quite important for the species we've been talking about, like birds and butterflies. There's also soil information from soil grids, and these are mainly they are referred to as environmental data, which ecologists rely on for their modeling.
Another data source you mentioned was satellite imagery. I'm not sure if you can see a bird in a satellite image, much less a butterfly. How are those useful to you?
That's true. Okay, so the idea was to detect this species distributions from their locations. A satellite image represents a location and also represents the habitat. So the idea of the habitat for a satellite image, it's like where birds can exist on certain buildings or certain cliffs, exist in cities or not. These were the kind of information we're hoping to get out of satellite images. Empirically, satellite images are helping, but they are not as much, not as we're hoping it would add to the model. Still, the main information come from the environmental variables, climate and soil information. Yes.
And what about the last one, citizen science data?
Yeah, citizen science. Citizen scientists are people, like normal people who go and people who do bird watching, for example, on the database called eBird. There is a mobile app or a website where people who go bird watching at certain times, they record their observations. We collect these observations and use this as the data source. It is a reliable data source and it's growing. And that's why we refer to as citizen science, because it's coming from citizens. For this work, we rely on eBird, a database for birds, and eButterfly.
Listeners, you know I love data, but not my personal data available for free on data broker websites. Are you inundated with spam or annoying robocalls? Where do you think they got your number? I get tons of robocalls, I really do, and anything that can move that in the right direction is something I need. Having your personal information on the internet is like giving strangers the keys to your front door. Thankfully, Delete Me can keep that door locked and keep your information safe. Delete Me finds and removes any personal information you don't want online and makes sure it stays off. Delete Me is a subscription service that removes your personal information from the largest people search databases on the web. And in the process, it helps prevent potential ID theft, doxing, phishing scams, and other negative outcomes. You sign up and provide Delete Me with what information you want deleted, and their experts are going to take it from there. Delete Me sends you regular personalized privacy reports showing what they found, where they found it, and what they removed. Delete Me isn't just a one-time service. It's always working for you, constantly monitoring and removing personal information you don't want on the internet. Take control of your data and keep your private life private. Sign up for Delete Me, now at a special discount for Data Skeptic listeners. You can get 20% off your Delete Me plan by texting DATA, D-A-T-A obviously, to 64,000. That's text DATA to 64,000. That's the only way you're going to get your 20% off. Messaging and data rates may apply. See terms for details. Just text DATA to 64,000 and Delete Me will help you become more anonymous online. Could you describe the species distribution problem? What is the goal you set out to do?
Okay, so species distribution, the idea is to predict the probability of encountering a certain species at a certain location based on some information. So whenever you go to a place, what's the probability of seeing species X at this certain location? There is a lot of work in using traditional methods in ecology on species distribution modeling and joint species distribution modeling, where the idea is trying to understand where species occur and how they co-occur.
Who's interested in that distribution? What types of consumers want to look at the results of a model like yours?
Mostly ecologists. What we're doing should help ecologists and eventually should inform policymakers and decision makers about the changes that are happening in our ecosystems. I believe there is still a gap between machine learning and traditional methods in ecology. It's one of the challenges. It's also one of our rules to try to bridge this gap somehow.
In sort of broad strokes, could you describe the modeling process? How do you go from raw data to the distribution prediction?
Okay, so we go into the process of data collection and preparation. So there are different sources for the data, as you talked, satellite images, environmental data, and the citizen science data. For satellite images, we collect the data from publicly available resources, such as Planetary Computer, Microsoft, or Google Maps, and so on. We collect and clean the data, and also for same for environmental data. There is World Crim and soil grids that we relied on. For citizen science data, we collected the data from eBird and eButterfly. I think that was the most challenging because we modeled the data in a way such that each instance of the data is a presence-absence data, meaning that at each location, the target, like our target, is to tell what species are present for sure and what species are absent. And this is referred to as presence-absence data. There is another setup called presence-only data, where we rely on which species are present. We prepared the presence-absence data, and these are our targets, our outputs, and satellite data from satellite images and environmental data are our inputs.
Well, you touched on eBird and eButterfly. For any listeners who aren't super familiar with those, could you describe them?
They are publicly available databases where they have thousands of observations on bird species and butterflies. So let's say you're interested in bird watching, you go at 6 a.m. in the morning on a weekend, some location close to you in a park or something. You saw a few interesting birds and you wanted to take the initiative and record your observations about these. So you would go into the eBird application, you will record your location and you record the observations you've seen. You can also take pictures of the birds you've seen and record those. There is a lot of data on eBird compared to eButterfly. That's a situation where there are abundance of observations about certain species compared to another, and this is where the value of our work on predicting using partial data comes.
Those both sound like good resources, but also maybe not perfect resources. What was the motivation to introduce SAT Butterfly?
Butterflies are also affected by like climate change and the environmental changes that are happening lately. There are no enough observations or enough data about butterflies, so they represent a scarce data source. And given that we have like a good data source of said bird that we already built, we wanted to like complement it with another smaller data set to be able to study the idea of predicting with using partial data and see how information about certain species will help us improve predictions about the other set of species.
Could you talk about the data cleaning process?
We spent some time like doing like further data filtering and the cleaning. We excluded data outside continental US, so we mainly relied on data inland in the US. We exclude data like in Alaska and Hawaii. We've also excluded data or species that have less than a certain threshold of observations, so we can have like reliable like data that we can model. Yeah, that's mainly the data filtering. But I'd say that's also like it's one of the challenges that mostly the data, the abundant data is only in the US mostly. There is also it's also in Europe, but you'll find that data in the global south is not as much.
Well, in ecology, I know co-occurrence is a common topic. If there's an anteater around, you can be pretty sure there's ants around as well. Can you take advantage of insights like that in trying to predict the species distribution?
Yes, that's actually the motivation that like having information about something will tell you about the other thing that you want to predict. So the idea of co-occurrences is something that ecologists rely on to predict species because yeah, it's true in wildlife that the species co-occur. Certain birds are there because of certain insects and or trees or butterflies and so on. That was mainly the motivation, and modeling co-occurrences is quite important. And we're hoping to develop a method that ecologists will use along with their traditional methods.
Well, in terms of methodology, could you talk a little bit about what you found useful? You'd mentioned that ML techniques are maybe underutilized. What's common and what's getting the work done?
We actually found that simple like ML baselines are really doing well, like using like just a simple MLP model over environmental data, or using a ResNet over satellite images. I mean, it's not complex like machine learning models as in the current literature. They're quite simple models. It's all about like how you model the task. Once we're done with like the data preparation and modeling the task itself, the modeling part of or the algorithmic modeling part was not the most challenging. So between different models of like MLP or using convolution models, I won't say that the gain was that much as we moved to modeling like using also partial data as extra information to predict like certain set of species. That's when we moved to like a more complex model that uses like transformer like units.
In a lot of machine learning cases, especially if we're going to do a train and test and maybe a holdout set, I need to know I have some access to ground truth, some labels that I can train on and validate with. Do you have a notion of ground truth in your work?
Yes, we created like our own notion of ground truth by splitting like after like collecting and preparing the original data. We kept a 30% split to be a validation and test. So 15% of it like were a validation set, and the rest like 15% was a test set. And this is what we report on in our work in the two papers.
And could you share some details on the performance metrics? How do you evaluate the quality of the model?
Okay, that's a good point. It's actually challenging. It's a regression task. It's a multi-label regression task. Normal metrics used in regression, such as like mean squared error and mean absolute error, didn't really represent that much. Like they are not much interpretable in the setup, and they won't tell you much about the performance. So they look good, but you don't know how good the model is doing. We relied on another metric that we defined called top K accuracy. There's also top 10 and top 30 and top K accuracy, and by that we choose the species that have a non-zero encounter rate, and we see if our prediction detected like how many of those species were predicted with a non-zero probability in our predictions. and the match will represent like the top K accuracy. So we use this accuracy to represent how good our models are.
What sort of scale is that on, and what kind of quality do you achieve?
It's a percentage. It's like accuracy. It's a percentage from like 0 to 100. Our numbers, like we always compared our numbers to us like a simpler model that uses only environmental variables. It's quite good. So I think the top we've achieved were like 66% compared like to a dummy model of just the mean encounter rates that achieves like around 45%, and then an environmental baseline that achieves 63%.
I think that's a pretty good milestone, but if you wanted to get it higher, do you need better data, better algorithms, or both, or maybe something else?
I think all is applicable, but one thing we found, like after the first work of SatBird, that satellite images are not adding that much, are not adding, as I mentioned earlier, they are not adding as we hoped it would add. Maybe because of the resolution, maybe because as you said, Gilk, you don't see much about birds in a satellite image, and you're also adding like more complexity to the modeling. Right now, in our follow-up work, we're relying less on satellite images and focusing more on improving the modeling like that relies only on the environmental variables. It makes the model simpler, but it will also help us like utilize environmental variables the most. There are also other sources of information such as land use and land cover data that we might add. Also, more data is always welcome. So your theory of like having more data is applicable. Maybe at this phase, like it's important to focus on what's really helpful for the problem. What kind of data is helpful.
And part of the work is introducing the RTRAN model. Could you share some details about what RTRAN is?
The idea is inspired from another model in multi-label classification literature called CTRAN, classification transformers. So what we did is we only adapted this model to the regression problem, of like the multi-label regression problem of species predictions. This is the second model that we developed for predicting species encounter rates with partial information. So we combined all the data sources we have, like the environmental data and satellite data, and we passed them into a ResNet 18 encoder. We also add label embeddings. We learn label embeddings over all the species. The most important part is what's called state embeddings. State embeddings, I like define what species are known and what is unknown, what species are there and what species are not there. And through learning these embeddings along with the label embeddings and the features that are learned from the ResNet 18, they all go into a transformer encoder that will predict the species that are only identified as unknown by the state embeddings. And this is a component that enabled us to like define what species we know information about that the model will use, and what species we don't know information about that the model will output predictions for.
Well, the transformer is a relatively new method, and it's obviously had great success in natural language processing, but I don't know that it's obvious it would apply to your situation. What gave you the idea to incorporate it?
As I told you, it's inspired from like multi-label classification, image classification literature. Transformers, yes, they are well known in NLP, but they are not like unique to NLP. They are now used widely in the computer vision literature. There is image transformers, but in this case, they are not used as image transformers. They are actually used like after the feature encoding part as a set of attention layers. Like they are still a helpful component that they are not exclusive to NLP.
Well, I know all of the embeddings in the transformer are obviously what allow, or parts of what allow RTRAN to outperform some of the other methods you looked at. But do you compromise on interpretability by adopting those? Can you still tell how the model's working?
That's a good point. One of the things that what we still need to do is to like provide further analysis on how species co-occurrence are really happening and how a set of species X is affecting a set of species Y. So I'd say yes, it's still some of the components are more of a black box, which is a clear challenge in machine learning, which is also a challenge that creates like a further gap between ecologists and like the machine learning world. Yeah, there's still more efforts to be done to provide more interpretability on that part. You're right.
And with regard to Satbird and Sat Butterfly, are these data sets that were assembled, for this project, or do you see it being maybe an ongoing effort?
For us, we're still actually continuing the work on that project. There are more improvements on the modeling part, and there are also other data sources that we're adding. For example, trees data that we believe will be helpful for like the set of birds and butterflies. But yeah, I can't share results on that yet. I think it should be an ongoing effort, regardless of like what we're doing now. It should be an ongoing effort. And one of the things we're really looking forward to do is to collaborate with ecologists to see how they can use what we're doing, because that would be the most impactful.
Well, the climate is changing, as you know. Does that present challenges for your work? Maybe by the time you've made a prediction, the everything's kind of evolved a little bit in this dynamic system. How do you deal with the complexity of change in the environment?
In some cases, I don't think it's changing, but the effect that you would observe in our different data sources, it's not that much. For example, like for birds data, we're aggregating data from 2010 to 2023. With this data, we're using only a a very recent satellite image in 2023. That may not be the best way to do it, but it's still possible because the change over time is not that much. I think we're more at a stage where we want to get more work done. We want to do more work in this area, see if we can help ecologists, decision makers somehow, and like just deal with whatever data sources we have for now.
Well, there's definitely a value in just basic science, right? To have these distributions of where species are. So certainly there's a value delivery there. Do you see that maybe there's something further, like could you impact policy, or should governments take notice of the work and take on certain conservation efforts? Are things going to move in that direction, perhaps?
Hopefully, you would want things to move in that direction. Machine learning should complement the different like biodiversity monitoring methods and efforts in that direction. That's why the like one of the best ways to go is to like have ecologists inform us like whether this really will help them or not, or how we can like tweak our work or our methods to make it more useful for them. Yes, the best case would be to be able to inform like policy makers somehow, and like governmental initiatives on conservation efforts. That would definitely be the way to go.
And earlier you'd mentioned that I guess I don't mean to put words in your mouth, but something to the effect of there are still good opportunities for machine learning to be having an impact in ecology. Could you share some thoughts in that direction? Maybe there's an aspiring young machine learning engineer who's looking for a good place to direct their talent.
Like AI is they hyping these days, and everyone wants to work with machine learning and so on. But this is really one of the applications that motivate me to continue like with the work in AI, because I like my work to have an impact, and it's one of the applications that maybe represent like AI for good, which is important. I believe is important. The few people that are working on these different areas, AI for climate and biodiversity or AI for good, they are truly like inspiring and motivating. And there are a few interesting works right now, not only species distribution modeling. So there is like species identification from like using like computer vision methods. You're just using images to identify species, or identify species using audio, like sounds of different species or birds or whatever. There's also the idea of having camera traps and for insects in the wild. So there is a lot of effort being done, and I think it's an interesting start for anyone who wants to do more impactful work in machine learning.
So do you expect that the machine learning techniques will replace the historical or, existing methodologies?
Like the idea is not to replace like using machine learning in these applications. The idea is not to replace basic methods or traditional methods. used by ecologists and policymakers. The idea is to complement, to make it better and like to make it faster and less costly, because like most of the field work and data collection and so on is costly and it's consuming a lot of time and efforts. But machine learning can work better with like a lot of like having a lot of data. It can process data faster, and the idea is to combine like our efforts in like on machine learning with like the field work and the expert knowledge in the community to provide like better understanding of biodiversity, better understanding of the changes that are occurring because of climate change.
And what's next for you in your work?
We're still like building up on this work, like hoping to transform it into like a journal paper, a more comprehensive paper where we're adding like other sources of data, like such as like trees data. We're still looking into if there is a way to co-locate the trees data with birds data and hopefully like train a single model that can predict both. And we're also like doing further like algorithmic improvements to the model itself to make it simpler. And maybe this will touch on like the interpretability issue that you've mentioned.
Well, even still, if it works, right?
Yes, but yeah, you don't want like ecologists to think that this is too complex and this is a black box that we don't want to use. So we should work more on the gap, like from our side.
And is this your primary focus, or are you involved in other projects as well?
Like, no, in the meantime, I'm involved with like in another industrial project that I can't talk much about.
And is there anywhere listeners can follow the project online?
We have a website for SatBird. We'll update it with the follow-up work once it's ready. The data sets are publicly available, the code is publicly available, and would welcome any follow-up work that uses the data. We also sometimes get emails from people who are using data and the code. They have questions, they have clarifications. Also, like they helped us fix something in the past, so these are always welcome. Like following the work, so it's mainly gonna be the website and Twitter.
Well, Hager, thank you so much for taking the time to come on and share the work about the project.
Thank you so much for the opportunity. It was really fun.